Hello everyone and welcome to the next session of Digital V Days. It's the last day of the Digital V Days. My name is Silas Zon and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of the day is Boost Your EMC Performance, Unleashing the Power of a Low Impedance Return Path. Our speaker today is Tristen Boeckx, who is working as a sales manager at Würth Elektronik ISOs. The webinar today is recorded and will be about 30 minutes long. After that, Tristen will come to the session and will answer your questions live. So you can enter all your questions in the Q&A tool at any time. So this can be found at the bottom of the page on the right side. So now I'm wishing a nice and exciting webinar, and we can start with the recording.
Hello everyone, my name is Tristen Boeckx. I'm an EMC debugging engineer based in Benelux. I'm specialized in debugging EMC problems, solving EMC problems for our customers. Due to this position, I was able to already gain a lot of knowledge looking at EMC. The reason that I want to present this topic is because I see that a low return path, a low impedance return path, is one of the biggest fail causes of problems with my customers looking at EMC. Further, by implementing a structured approach, you can transform EMC from black magic into a predictable science. If we implement this in an early stage, you will not only provide a clear path for troubleshooting EMC issues, but you can also this can also lead to a significant cost savings and time savings within the project. Today I want to go deeper in following topics. I want to go into an introduction in the theoretical basics. I want to see at the influence of bypassing and blocking, some PCB design tips, further some practical examples, and at last a short summary. First, I want to zoom in on a basic principle of the current flow. By looking at this schematic, we can see when we are closing the switch that the current is flowing in a loop. When we have the same schematic as before, but the lowest part replaced by grounding symbols, as it is widely common on PCB schematics, some design engineers tend to think that the current is disappearing in the black hole. And it not only disappearing in a black hole, and that it is not more than a reference point or a silent ground. But in fact, we changed nothing, and the current will continue to flow in the same route as before. When having this in mind, it is interesting to zoom in how this current will flow depending on the frequency of the signal. In the schematic, we can see a representation of two ICs placed on a PCB with in red a signal layer that connects those two ICs. On the bottom layer, we see a green ground plane, and when we start on a frequency of 0 Hz or DC, we can see that the return currents in white are spread all over the ground plane, but taking for the biggest part the shortest route. This is due to the ground plane's low resistance. Further, when we increase the frequency, we can also see an increase in the return currents flowing below the signal path. This is due to the higher frequency, that at a higher frequency also the inductive part is showing to be more dominant. The path of the least inductance or impedance is the shortest loop area, and this is of course below the signal trace. At the frequency of 10 MHz and above, we could say that the return currents are almost fully flowing below the signal trace. When then facing a slotted ground plane, the return current wants to retain the shortest loop area below the signal path. When facing the slotted area, it will flow near the edge, what can create problems in a later stage looking at EMC. Of course, this is always interesting from a theoretical approach, but the nice thing is that we can prove this by a small experiment. When you look at this setup, we can see on the left an oscilloscope with an integrated signal generator. The signal generator was connected to a transmission line, as shown in the middle, and was set to generate a 20 MHz square wave signal. Further, on the input of the scope, we connected a magnetic field probe. If we start measuring at the edge on the top, we will see no signal. We will measure no signal from the signal trace. When approaching the signal or the transmission line, we will be able to detect the return current as shown below in the left bottom picture. If we then introduce a slotted ground plane, we will detect the return current on the edge of the slot. Not only this, but also it's not ideal, as can be reviewed below, because there is a 15 dB margin difference, so a higher measurement. What proves the theory mentioned before. When we zoom in on bypassing and blocking, I like to explain this topic by a drain pipe principle. If we zoom in at first in a blocking element, then we can see that when water is entering a blocking element, we can see that the water is blocked. But when the amount of water is big enough or bigger, then we will see that the blocking element will be overflown. And this can create problems. When looking at the bypassing element, the water will flow down, but if the water increase or the amount is getting bigger, then also the water will flow from the wrong side. When combining both the bypassing and the blocking element, the water is forced to flow down as intended, and also when the water amount is rising. When we make the translation from a drain pipe to a PCB, we know that blocking elements introduce a high impedance. Some examples are inductors, common molder chokes, ferrites, a lot of different components, but also parasitics like traces, wires, and so on. When we zoom in on bypassing elements, they are introducing low impedance pads, low impedance, and the most common one is a capacitor. But also for high voltage types, a surge or ESD protection can be a low impedance return pad. I like to start from a use case when creating a bypass at 20 MHz on your PCB to decouple an IC. I want to start by selecting an appropriate component. As seen, a capacitor is an interesting component to do this. For this, I start in a RedExpert tool by searching the lowest impedance for the requested frequency of 20 MHz. In short, RedExpert is a searching tool of Würth Elektronik where the data of a big amount of components is collected. The nice add-on is that the RedExpert is using measured data, therefore all the parasitics are included in the search. When looking at our case, using the slider and sorting on the lowest impedance, I'm able to find that the 150 nanofarad is an interesting value to use. A real capacitor is built up from a C, a capacitance, an ESR, and an ESL. Also, these values can be found in the RedExpert tool when needed, and as shown on the right, not only the value of the capacitance is important when you search for a component, but also the footprint is important. Like you can see, the bigger the component, the higher the ESL and also the parasitic inductance. First on the left, we see both above and below a longer trace. This introduces an inductance but creates at a higher frequency an impedance, which will cause that the component or for example, the capacitor won't be able to work as well as intended. If we look at the middle picture, we can see that the routing is done better. There is no longer an inductance above and below the component, but there are still long traces. If we look at the right, this is the best way because there is the lowest inductance or impedance introduced. When we then zoom in on the same topic, we can see on the left side that there is again an inductance induced, what creates an impedance. Also, as you can see on the right, it is better to place multiple vias connected to the IC, connecting ground planes or voltage planes. On this slide, I want to show that the PCB needs to be seen in 3D. For example, when looking at this drawing, when changing layers, there is a change in impedance. This can introduce ringing. This is also one of the important reasons to avoid vias in high-speed clock lanes, and that is often an EMC problem. When reviewing the layout, we can see that the upper design has a lot of unnecessary inductance impedance. Also, there are inductive couplings between the traces and capacitive couplings. Further, there is also an inductance shared by the return pad to ground, so this introduces a lot of parasitics. When we then make a better layout, we will see by removing these parasitics that we will be able to also make a better performance filter. To give an idea how big those parasitic impedances of the inductance are, we use a frequency nomograph. This is a graph to quickly identify the corresponding impedance value of an inductance or capacitance. The horizontal lines are showing the impedance, the vertical, the frequency. The diagonals starting in the left top corner are the capacitance, and starting on the right top corner are the inductance. As a rule of thumb, we can say that every centimeter of trace cable is 10 nanoharries. As we put this to the test, we can see starting from a 10 nanoharry inductance at a frequency of 100 MHz that we are having approximately an impedance of 7 ohms. When doing the same mathematical approach, we can see that this almost 70 ohms. To put this in practice, I made two PCBs, one with the capacitor shorted and one where a 1 centimeter wire is placed between the capacitor and the ground plane. As can be reviewed, by introducing the wire, the filter is less strong, so the conclusion of this test is not only search the capacitor with the lowest ESR, but also take the layout into account. A short summary looking at this, we can say that the high frequency currents are fed from the capacitor, that both the ground plane as the power plane only see low frequency currents due to the high frequency currents are fed through the capacitor. It's important to keep the magnetic loop for RF as small as possible. Also, of course, it means that the distance needs to be as short as possible. Further, a low impedance connection to the capacitors with less inductance is interesting. And it's important to keep the line symmetrical if possible. And an extra tip can be that you place extra vias in parallel, so there is a least impedance showing up to this system. When we then zoom in on immunity design tips, we can say, for an example, when we have a PCB connected, mounted on a chassis, conducted chassis, and we introduce an ESD, then it's important to know how the current is flowing. In the first example, you can see that the current will flow like this, and this can introduce disturbances that affect the electronic parts. When we then place it shorter to the TVS, then we can see that the return path of this ESD pulse is better because it doesn't disturb the PCB or the other electronic components on the PCB. If we then see on the following setup with an I/O board that is connected to a main PCB, it's important to place the ESD protection nearby the I/O board, so the disturbance won't flow through the cable and won't generate any noises. If we then have a look at EFT, or electrical fast transient, what is a main or is a well-common problem in EMC, then we can say that an EFT is a high voltage, high frequency noise. This is due to the high or steep edges, but gives this a wide frequency band noise signal. If we then look at the EFT test setup, we can see that there are two different noises introduced. As first, we can say that there is a differential mode noise introduced. This is showed with the blue arrow, blue line. Further, there is also a common mode noise that is induced on all the three lines, and that runs through a capacitive coupling back to using the ground plane back to the source. To reduce both differential mode noise and the common mode noise, we are in need of applying some components. For the differential mode noise, we can first look at an X capacitor that's bypassing the differential mode noise. Further, for the common mode noise, we can say that both a common mode choke or Y caps are the best solution to prevent the common mode noise. It's important to look at the base frequency or the starting frequencies of the EFT. These are both a 5 kHz signal or a 100 kHz signal to select your filter. A nice add-on could be to replace or to add where the resistance is to also a resistor. And a last small tip is that the leads are needed to be as short as possible to have less parasitic coupling to other parts of the system. When we then zoom in on some practical examples, I had a customer that was failing the radiated emissions. As can be seen on this picture, we have both a controller PCB and a display PCB that are connected by a ZIF connector or a ZIF wire. When we then zoom in, looking at the theoretical approaches that we had in this presentation, we could say that the traces are an inductance and also an impedance. Due to this difference, due to this impedance, there is a voltage, and this voltage drops introduce an antenna made of both the ground plane of the controller and the ground plane of the display. By disconnecting the display, we were able to see that the full antenna was removed and there were no radiated emissions anymore. But of course, the customer needed his display, so we had a look to see how we could solve this. By providing a low impedance return path using the mounting holes, using a spacer or an earthing belt, we were able to pass the customers with about 10 dB of room or headspace with the standards. The second example was from my customer that with quite the same setup had a PCB where a display was mounted on top. Due to the inductance of the cable, there was a voltage difference between the ground of the controller, but also a ground of the display. Further, there was also the noise of a DC-DC converter that was coupled in the ground plane of the display, and therefore there were a lot of EMC troubles, as can be seen on the right. By applying on the left side a gasket and on the right side an EMI finger, we were able to provide a low impedance return pad and also provide the customer with a solution that he passes the limits or passes the standards. At last, I want to make a short summary of the 4 most important points from my perspective. First of all, currents are always flowing in loops. Further, at DC side, resistance is dominant. At high frequency, the impedance is dominant. To control this, it's important to use bypassing or blocking elements, and if needed, both. And at last, it is important to always identify the parasitics. Hopefully, those 4 rules give you the chance to pass the EMC measurements in the nearby future. Thank you for your attention, and if you have any questions, I'm happy to answer them.
Yeah, thank you, Tristen, for the nice presentation. Now, hi, Tristen. He's joining to the session, and yeah, now we would like to turn our attention to your questions and start with the short Q&A session. So I think we can directly start with the first question. How do I implement in an early design stage a low impedance return BEV?
Okay, yeah, that's a good question. From my point of view, there are 2 stages. In the first hand, in the first stage, we look at the schematic when we have a block diagram. Then I look with my customer to have the potential noise sources in the system. For example, this can be like a DC-DC converter or high frequency clocks in the system. So I want to point them out and already provide some filtering to them. In a second stage, we move to the PCB design, and then in that stage, I want to look at those already pointed important parts of the schematic, that they are well designed without big parasitics, like as seen in the presentation, 1 centimeter trace or something else. So that's, I think those 2 stages are important.
Cool, thank you for the answer. Yeah, next question. What is the best way to simulate by passing, blocking elements in a schematic?
It depends. In an early design stage, it is interesting to use, like, for example, our RedExpert tool, because you can also simulate there the input and output impedance to select your components. Also, we have an EMI filter tool where you can already put some parasitics from the components, like the DC bias effect of a capacitor inside. And in the second step, I like to use LT Spice from my side, because all our products are already in these libraries, and we have also extra libraries looking at, for example, common voltage shocks or something else. So it's in the first hand I use the RedExpert tool to make the first selection, and after that I make a system level LT Spice simulation.
Thank you, Tristen. one information I forgot it at the beginning of the session. You will all receive the link to the recording and to the presentation after the webinar via email. So now we continue to the next question. When to use a bypass cap or an inductor chip beats? Is it dependence on my source and load impedance?
Yeah, I can also see the question in inside the question and answer dialogue. Yeah, when to use it? It's hard to say because not every noise will make an antenna and will radiate. So from my perspective, I would always place them in the early design stage, because if you need to put them afterwards in, that's mostly of the time quite hard. And of course, it depends indeed on the source and the load impedance. But the nice thing is that you already can simulate those things with our Red Expert tool. So I would say just place them already, make those points, look at the frequencies that are a problem inside your system or could be a problem in your system, and provide a low impedance return pad using a bypassing element capacitor that is selected, and also a ferrite to extra push it inside the capacitor.
Perfect, thank you. So I think we come to the last question. There's no more questions in the Q&A tool actually. What would you recommend to follow when designing clean earth for an MCU?
I think there's not really a clean earth, I would say, but from my experience, the best way is just to have a single ground plane that is not interrupted, and that you provide all the return pads with the shortest possible connection to that ground plane. So that would I recommend to use.
Thank you. One last question comes in. One more question comes in, sorry. In bypassing, are wire in pad more effective than multiple wires near the pad?
Yeah, there are a lot of theories looking at layout design examples. Yeah, it depends on the component, I would say, but maybe it is nice that I can answer that question by email, and I can already give some layout guidelines with some schematics nearby, and also with a plot looking at the different effects of those connections.
Okay, thank you, Tristen. So one more question comes in.
Of course, no problem.
We can continue with that. Parallel caps for different frequencies. Is that going, yes or no?
That's one question that a lot of engineers say yes or no, so it depends on who you ask. From my experience, it's better to select one good capacitor with a low impedance or low resonance frequency on the wanted frequency, and then place those two of them or three of them in parallel. So you have no extra resonances in your system, but due to the parallel of those systems, you get an ESR that is less, and that gives you a better return pad. So from my experience, it's better to place two the same caps with the same value in parallel, and make this of this type of return pad, low return pad.
Okay, thank you, Tristen. So I would say last question. What should be used for IC square between two boards?
Yeah, I think the nice thing is, maybe I can show you. I need to see if we have provided it on our website, because we have now, since short, we have a nice extra page on our website, and I don't know if, yeah, okay, I will share it with you guys. Can you see my screen?
Yes.
So maybe in short to see to show how I got there. We have here our landing page. We go to applications, application guides. We have here a lot of applications. If we then look at the data lines, we can see that here is I2C inside. And then we have a full recommendation using I2C and also some application notes. So I would recommend the person that requested this question that he has a look on this page and see inside the application notes what can be used. So for here we see that there are ferrites used and also some ESD protection inside the system.
Yeah, very cool, Tristen. Thank you for all the answers of the questions, and thank you too for your time and for the interesting presentation. So yeah, thank you for your all attention. I hope you enjoyed it, and hopefully we see you on the next session of Digital Weekdays. So yeah, I wish you a nice day, and bye bye.